The lab exercise we're beginning now is going to utilize a chemical skill and process known as titration. Titration is something it's oftentimes used to determine the concentration of some unknown solution. Titration typically uses a device known as a burette, which allows us to very accurately measure a volume of solution that's been incrementally added to some other solution that typically has some unknown concentration. For our purposes in this lab, we're going to be doing a series of titrations where all of the reactions are going to be an acid plus a base. Now, all acid-base reactions are going to create the products of a salt plus water. Also, acid-base reactions are a form of a double replacement reaction. For example, hydrochloric acid and sodium hydroxide, it's a double replacement. The positive ions will trade places, and we end up forming our salt, sodium chloride, and HOH, which is the same as H2O, would be our water that we form in the reaction. Or another example, nitric acid and lithium hydroxide. Again, we'll trade places with the positive ions. We generate our salt, which in this case is lithium nitrate, and our other product will be water. An example of a titration would be something where we may have an NaOH solution of some known concentration and something such as HCl of an unknown concentration that we're trying to determine. The burette allows us to open the valve and dribble in the sodium hydroxide to the hydrochloric acid until the hydrochloric acid is completely neutralized. In titration terminology, once the acid and base have been neutralized, this is referred to as the equivalence point. Typically, at the equivalence point, this would be when the moles of acid are equal to the moles of base. This would be true in a reaction such as the HCl and NaOH, where they react in a 1-to-1 ratio. In addition to the equivalence point, we need some visual clue to tell us when the moles of acid and base are equal, or when the acid and base have been neutralized. An indicator is oftentimes placed in the solution which experiences some sort of color change. The color change occurs somewhere in the vicinity, the pH vicinity, of when the acid and base have been completely neutralized. However, when the desired color change occurs, in titration language, this is known as the end point of the titration, in that when the color change occurs, it tells us to stop the titration, crank the valve closed to stop adding additional base. We try to match the color change that occurs such that the indicator solution used makes the color change occur in concert when we're close to being at our equivalence point. Let's take a moment and go through a sample calculation for part 1 in the lab when we're standardizing or figuring out the concentration of our unknown sodium hydroxide. The NaOH solution of unknown concentration will get placed in the burette. In the flask, we're going to place in a monoprotic acid, which is abbreviated as KHP. KHP is the same as potassium hydrogen phthalate. It's just an abbreviation for potassium hydrogen phthalate. For our purposes, a key part of KHP is the known quantity that KHP has a molar mass of 204.23 grams per 1 mole. This allows us to very accurately measure out how many grams we have in our flask, which lets us accurately determine how many moles of our monoprotic acid are present in the flask. Our given information in the problem tells us that we're utilizing 14.5 milliliters of our sodium hydroxide solution to neutralize 0.27 grams of KHP. Is how much KHP we've placed in the flask and dissolved in the water. We can use the grams of KHP that were used to set up a proportion. We know 1 mole of KHP has 204.23 grams, so there'll be X moles of KHP present in our 0.27 gram sample. Solving for X gives us 0.0013 moles of KHP got neutralized by the addition of our sodium hydroxide. Because KHP is a monoprotic acid, meaning it has 1 hydrogen to get neutralized, the sodium hydroxide and the KHP react in a 1-to-1 ratio. This allows us to now say, since we know we have 0.0013 moles of KHP that got neutralized, that means in our sample we also have 0.003 moles of sodium hydroxide that were used to neutralize the KHP. So what we now know is this quantity, 0.0013 moles of sodium hydroxide, that's what's present in the 14.5 milliliters of sodium hydroxide that we utilized to neutralize the KHP. This information allows us to set up a proportion. We now know that we have 0.0013 moles of NaOH in our 0.0145 liter sample. That'll allow us to calculate how many moles of NaOH would be present in a 1 liter sample, and once we have this in terms of moles per 1 liter, that would be our measure of concentration. Solving for our concentration, we find that for this particular trial, our concentration of the sodium hydroxide is 0.090 moles per liter, or 0.090 molar sodium hydroxide.